Good evening, my lovely people. We're going to look at a vertical circle question and hopefully get to a horizontal circle question as well, and both videos should be up soon. I'm going to try writing this. Hopefully the video won't crash too much. So when we're dealing with circular motion in general, we have to remember we have our physical concepts of a reaction being balanced by an opposite reaction, gravity down. If it's horizontal, if the circle's horizontal, then all the ups equal downs, and any left-right forces have to result in the circular motion force, which we have from the tables. If it's a vertical circle, it's slightly different and this question I'll talk through why it's slightly different, but hopefully it'll still make sense and just to be able to apply our circular motion knowledge, because we still have our circular motion force, we just have to look at it in a different way. Because what's happening here in a vertical circle is the mass is changing its position relative to the Earth. It is, in this question, it is moving towards the Earth's center of gravity, which means its potential energy due to gravity is decreasing. And as its potential energy decreases, because we have conservation of energy, its total energy staying the same means that its kinetic energy has to increase. There's a snowboarder question, which is the opposite. Where a snowboarder comes in, it would have no potential energy, and as it goes up the half pipe or quarter pipe in the question, I think it is, it would have to gain potential energy as the snowboarder went away from the center of the Earth, which meant it has to lose kinetic, so it slows down, which is kind of intuitive anyway, but that's what's going on. So I will talk about this one. If you then try the snowboarder question, I can't remember what paper it's on, 23 maybe, or 24, and you want me to go through it, I'll happily throw up another video. It'll be the same concepts, but it might be good to see what's going on. Now, when I prepped for this one, I made one very simple mistake in the algebra, which again threw off everything. I won't make that mistake now. I'll just highlight where I did, because I thought I was being clever and I just left out something. Right, let's have a look. So a smooth cylinder, radius 1.5, so ours 1.5, lies on its side in a fixed position on horizontal ground. So the cylinder isn't moving, that's good. Okay. Diagram of a circular cross-section of the cylinder shown below. The point of contact of the cylinder with the ground is fixed at point P. A small object of mass m rests on the highest point of the cylinder vertically above P. The object is slightly disturbed from rest so that it begins to slide down the cylinder. So basically it gets started with as small an amount of push as possible, so essentially zero. So we don't take any initial velocity into consideration. It is just put out of balance so it slides down, because there is a kind of an equilibrium up there where the mass is perfectly balanced on the very top of the cylinder. It's called an unstable equilibrium, like the top of a hill is unstable, whereas stable equilibrium is at the bottom of the hill. This is probably beyond applied maths, but you never know what they're going to throw at us in 6 days' time. So it's nudged slightly, so it starts moving, and then it moves along the surface of the cylinder, and at some point it's going to move, kind of leave the surface of the cylinder and just fly through the air until it hits the ground. But until that moment, it is moving in a vertical circle. What we have to remember, though, is with our circular motion, with our horizontal circle, in order for it to move horizontally, the horizontal force on it has to be exactly mv squared over r, what the centripetal force. But in a vertical circle, all that matters is that the body will stay, the M here will stay on the surface of the cylinder here. Our mv squared over r shows the maximum speed that can be happening in order to stay on. But as long as the thing isn't going past that maximum speed, it will sit here. When we look at the force diagram, it'll sit here until at some point it starts going too fast, and it then turns into a projectile and hits the ground somewhere here. So our mv squared over r is kind of the maximum it can be going to continue in a circle, i.e. continue on the surface. And as soon as the force of attraction in is less than what the mv squared over r needs to be, or is when we work out mv squared over r, then it will, give me 1 second. Damn, sorry, pause didn't quite work, and then it did, and then it didn't. So what's happening is this thing is going to be pulled into the center of the cylinder by an amount that is more than mv squared over r, until it isn't, and at that point is when it leaves the surface of the cylinder. So I will talk through it as we go through. I just wanted to give a bit of a heads up about what's going to happen, because what's happening is we have some forces pulling this thing in, and as long as the force inwards is bigger than our mv squared over r, so long as that's happening, it will stay on the surface. But as soon as v gets too big, the speed it's going at is too big, so that mv squared over r is bigger than whatever the inwards force is, then it leaves the surface and we have projectile motion, I assume. So just give me 1 more second. I'm walking the dogs in the evening and summer and hay fever do not mix. Right, so what we have is this situation. So we're going to see what the story is now while the thing is moving in a circle, i.e. the forces inwards are going to be bigger than our mv squared over r, and then see how we can use that to do whatever we need to do. Okay, cool. So that's where we're at. Student wishes to model the initial motion, so this modeling cycle is going to be in question. Outline the assumptions made by the student's model. So outline the assumptions. Now this is something I initially had trouble figuring out how to give some assumptions, and I kind of just started with something that I wasn't sure was right, which was no friction, because it says smooth, so I just put in no friction in case that was correct. It may not have been, but actually the marking scheme said it was. The mass doesn't roll, so is one thing I put in. So the mass slides down the cylinder. Doesn't roll, because rolling might be something else altogether, so who knows what that would be. So I'm just hoping that isn't the case. No wind resistance, so no wind resistance. All the energy, all the potential energy is converted to kinetic, i.e. kind of none lost to friction, sound, etc. So there's some things. Now this was 5 pointers, so I would say 1 would have got you 3, and then 2 would get you 5 points, or 1 would get you 4 probably. One of those things, one of the assumptions. So that's very vague in the marking scheme, but it's something like that. So just what would the assumptions be? And it took me a while to get on a roll with that, but stuff like that is what you're looking at. So calculate the value of theta when an object leaves the surface of the cylinder. Okay, so what I would do first, instead of trying to understand that, know that we're going to have to do our equations. We're going to have to figure out our model for the motion of that thing as it moves down the cylinder. So let's look at that first. So I'm going to just draw on this diagram. So what's going on here is that the total energy of the system is the potential energy plus the kinetic energy. So some places do PE, KE. I just prefer this. It feels neater to me. So the potential energy is mgh. It's in your tables. And the kinetic energy is a half mv squared, is in your tables. So we write that down because that's what we know we're going to have to work with. So let's look at the physics of what's happening here. Again, don't worry that it's on a circle yet. We have to understand the physics of what's happening. So at any moment, gravity is pulling it down. So that's mg down. It's moving with a certain speed v, perpendicular to the radius, and there's a reaction. There's no friction, so that's good. But what I think a mistake people make a lot is that they forget we have another really important piece of information, which feels like it's sneaky or just kind of. I remember being uncomfortable when we were doing this, when I was doing even though it has back in the previous century. If we draw that horizontal there, this I'm going to mark in yellow. We know that's the radius. The thing I've marked there, the radius. But we also know that that's the radius as well. We know the radius is 1.5. So the radius is the hypotenuse of that right angle triangle we've made using the red lines. So what's going on here is that this distance, that the height of the mass above the center point of the circle, is 1.5 cos theta. And it's using that triangle there that we can look at understanding how the potential energy is changed and then how to relate that to the kinetic energy. Because we know the potential energy at the start is mg by twice the radius. It's up the top here. So when the mass is up here, it has height 2r above the ground. So that means its potential energy, the h is 2r there. And we also know that the velocity is 0. So at the start, when our velocity is 0, all the energy is potential. Then it's pushed slightly to just get it started. And as it moves down along the circle, the potential energy it loses, because as it goes closer to the center of the Earth, gets turned into kinetic energy, which is our v squared here. And that v squared, even mv squared, looks very similar to our circular motion equation, which is F equals mv squared over r. So I think we're going to have a very nice kind of friction-free, ignore the pun, way of calculating what's going on here. So first thing we need to do is, what is the total energy at the start of our system? Now in a question, like even on Tuesday, it could be that it is given a push of 10 meters per second or whatever. So you'd have to build that in. You'd have to look at what is the V at the start. In this case, the V is 0. So first thing we're going to do is we're going to get initial energy. So initial energy. So the initial energy is E equals m g by 2 or. Now or was 3, wasn't it? Or was 1.5. So I'll write that down, just or equals 1.5. So our initial energy was mg by 3 plus 0, because there's no kinetic. I just write it down just to remember to write it down. So the energy of the system at the start is 3 mg. And that means the energy of the system while it's moving in a circle the whole time is 3 mg. So as our potential decreases, our V goes up, but they always sum to 3 mg. So what do we do then? We then look at the situation at any point as we go where we've gone through an angle theta. How has that changed our height? And then how has that changed our kinetic energy? We can put those together to find an expression for the potential, and then we see what happens. So just thinking about the energy, there is one little consideration I have to make, but that's how to determine when theta happens, but we'll get to that in a second. So in terms of the total energy is mg by something, and we'll figure that out in a second, plus a half mv squared. And the v is going to be the velocity I think we're going to want to find or do something with. So we'll see. So what is the height of the object? So the height of the object is this distance here. So how do we calculate that? Well, we know that that is or, which is 1.5. We've already written that that's 1.5 cos theta. So that's our height. It is 1.5 plus 1.5 cos theta. So that is our height, our h in our mgh equation. So the h is 1.5 to get up to the center of the cylinder plus our 1.5 cos theta. So that is our total energy at some, or at any point really, while the mass is moving downwards on the cylinder in the circle. But we know that energy is conserved, so this has to be equal to 3 mg. So what that means now is we can do something. I don't know what we can do, but we can do something. So what I would do with this is, well, we can divide out the m, can't we? Yeah, okay. I'm not sure how we're going to figure out how to circleify this, but we know this is true. So we can divide out the m. We can work this until we can do nothing with this, then start worrying. So that is, let's multiply everything by 2 then to get rid of that half. And that goes to 3g plus 3 cos theta plus v squared equals 6g. And then that would mean v squared equals, v squared is 3g minus 3g, I've got a g there, 3g cos theta. So this means that v squared, if you wanted to simplify it so you can kind of see a little pattern, but you don't need to do that. So v squared is that. Okay, that's something. It gives us something to work with. It will enable us to deal with the v squared when it gives us our v squared in our mv squared over or formula, I guess. So we now have to think, what is going on when, if we look at our diagram again, we need some kind of circular motion thing going on. So what's happening? Or is our reaction mg down? We haven't broken up the mg, have we, into this stuff? And that's our theta again. And our diagram's getting messy, and I probably should use a different color. That's our theta. So the gravity that's going into the center of the circle, the force that's causing, or the amount of force that's causing our circular motion to occur, is mg cos theta. Oh, don't forget, we have to take away the reaction as well, because that's pushing out. So the force due to circular motion, the F equals mv squared over r, is mg cos theta in and or out. So let's write that down and then see what happens. So our F into the center of the circle is mg cos theta minus the reaction, because they're the forces that have to balance out, or that they have to result in the circular motion, not balance out, because there is an imbalance. And that has to equal mv squared over r, or m omega squared. But chances are we don't need that. So, or don't need it yet anyway. So now here's another conceptual thing: is the mass is moving down the circle. It's moving in circular motion. As soon as it stops moving in circular motion is when it lifts off the surface just an infinitesimally small amount. So it's gone down that way, and it's just lifting off. What actually is going on there? What's happening there is the reaction is going to zero. The mass is no longer touching the circle, so if it's not touching the circle anymore, it is not moving in a circle anymore. So we can say that when reaction is zero, so when r is zero, this thing will let me do it. When r is zero is when circular motion stops. So what we have to do is put r equals 0, and that tells us that mg cos theta is equal to mv squared over r. So at that moment, when the forces in are exactly equal to the circular motion force, that's the instant at which circular motion stops, and the particle just becomes a projectile. So, but we know what, so we can cancel the m out on both sides of this anyway, that's good. And we know r is 1.5, don't we? So that's 1.5. But we know what v squared is. V squared is 3g by 1 minus cos theta. So this gives us g cos theta equals 3g by 1 minus cos theta all over 1.5. And this is correct now, I'm confident of that. But what the mistake I made was I forgot to put the 3 in. I was just so fixated on that, oh, I didn't need to square root the v squared to get v because it's already v squared, so that makes it nice and I can save myself loads of time. But I forgot to put that 3 in. So I got all my answers wrong, but again, that would, as in with the previous video, that would have given me lost me, say, 3 marks, or maybe even 1 mark, because it was an algebraic blunder rather than a conceptual one. So now, where are we at? We divide both sides by g. And that then gives us, sorry, I was second guessing myself, 3 over 1.5 is 2. So that goes cos theta equals 2 minus 2 cos theta. Bring the 2 cos theta over, that gives you 3 cos theta equals 2, which means cos theta equals 2/3, which means theta equals cos inverse of 2/3. And that's what the marking scheme wanted. I don't like trusting that that's what the marking scheme wants, but we will just get the answer here. So it's 48.2 degrees, 189, but 1896. So that's essentially 0.2. So that's how we get cos theta. Just to recap, in a vertical circle, we have to look at energy, kinetic and potential. We will have some way of understanding the total energy at the start of the system, total energy of the system at the start, and then relate that to what the energy has to, or use that number to relate our V and our H and our theta for some situation later on in the system's progression. So that's where are we? So total energy, that's one of the things we have to do in a vertical circle. The other thing is when it gets interesting, when it stops moving in a circle. So in this case, it was when the mass launches off the cylinder and starts flying through the air. In the snowboarder question, it's to do with how fast is it going when it leaves that quarter pipe, and then what happens then later due to calculus or something. So you'll see it and you should be able to deal with it. If not, just let me know. So then we have, this is the situation here. What is the condition or the thing that changes when circular motion stops? And in this case, the mass lifts off, so the reaction goes to 0. And when the reaction is 0, that's the instant circular motion stops, and gravity, it's just, the particle is just flying through a gravity well. And then we get the answer, and this is what the marking scheme said, and probably so that we use that cos inverse 2/3, or cos theta equals 2/3 whenever we're using cos theta later, rather than putting in cos of 48.2 everywhere and getting an inaccurate answer. But let's see, what is it that we actually have to do? Okay, so what we have to do is calculate the velocity of the object when it leaves the surface of the cylinder. So we know it leaves the surface of the cylinder when cos theta is 2/3. So we want to know V when cos theta is 2/3. So V when where are we? Cos theta equals 2/3. Can't hurt to put this stuff into short maths language, just to help you kind of turn it into something that you're happy working with. So we know V squared. How don't we? We do. V squared is up there 3g by 1 minus cos theta. So I'm actually going to revert to typing just because my OBS is not enjoying this. V squared equals 3g by 1 minus cos theta, I believe. V squared is 3g by 1 minus cos theta. Cool. And we know cos theta is 2/3 because that's what we got as our answer. So we know then V squared equals 3g by 1 minus 2/3, which is 3g by 1/3, which is g, which means V equals root g. Annoyingly, I got an even nicer answer when I did it wrong, so I thought I was perfectly correct. But I couldn't, I assumed everything was bang on because it worked out so nicely. So V is that. So the only problem that's not the velocity. That's it's not the velocity of the object in terms of i's and j's. Which it doesn't say in terms of i's and j's here, so actually leave it. So it just says calculated velocity, so we just have the velocity is that. And just to make sure we get full marks, it's meters per second. No, meters per second. Okay, so what's the next bit then? That's that. Okay. So the student models the motion of the object after it leaves the surface of the cylinder as projectile motion in a uniform gravitational field. So what's happening is my computer is very, very not happy with me. So that's why I presume my videos are jumping all over the shop. So we have the surface here, the mass is here. We know that angle, and we know it's V in that direction. And we know what V is, and that's, so I actually put in root G. So it's root G in that direction. So it leaves the object then. So what do we, in terms of projectile motion, what do we need? We need to know the time between when it leaves the object, leaves the surface of the cylinder, and when it hits the ground. So we need to know the speed it's going at and the height it is above the ground, because thinking of your projectile motion stuff, let's pretend that's a circle. We're going to start here with a ux and a uy, and we're going to calculate how long it takes to get to that distance sy. So that distance, we have that already actually, don't we? So we have here, if that's 1.5 and that's 1.5, this is 1.5 cos theta. Apologies for my awful penmanship, but I don't have to sit in an exam, you guys do. So we want to know how long it takes for the sy to be minus, because it's moving downwards, minus 1.5 plus 1.5 cos theta. Because when sy is that's when it has hit the ground. So all we then need to do is figure out what Vy is, and then we can just we can use our what's that, not Vy, so I suppose uy is what's important. The initial speed in the y direction. So how do we do this? So we know it's root g is the hypotenuse. Yeah. So we go straight down for our uy and straight across for our ux. Now what's the angle? Here's where you're going to have to convince yourself, I think, of what the angle is. So if we looked at it, we know that's theta. Because of the alternate angle z thing from maths, that's theta. Which means this bit is 90 minus theta, which means that's theta there. Cool. So uy is, it's downward, so it's minus. The hypotenuse is root g. And it's the sine of theta because it's the opposite. So root g sine theta. Now, if this was a projectiles question, I'd be finding ux and a, and I'd be writing everything out nice and neatly, so that I'm going to need it. So because I'm going to need it. But this one, I reckon we can get away with being as short as possible. We just want to find uy, so we just want to find sy, so let's do that. So from our equations of motion then, sy equals ut plus a half at squared. So it's minus g sine theta minus g over 2 t squared. That's our general equation for our sy. And we want to know what happens when that equals minus 1.5 plus 1.5 cos theta. Now, if you're looking at the marking scheme, it does this with positives, but it's the same thing because the negatives will all cancel out. Again, the marking scheme is designed for teachers and the examiners. It's not designed for you guys. It's never or rarely it's always the quickest way to get to the answer, and it's not necessarily the way you're going to do it in an exam. So let's put these things equal each other. So minus 1.5 plus 1.5 cos theta. Knowing that I know what cos theta is, I'm just putting this stuff in here first before I do anything. So that's your sy, so that should have been g sine theta t. So minus root g sine theta t minus g over 2 t squared. And well, we can get rid of the negatives there. Okay. We know cos theta is 2/3, so that is 1.5 plus 1.5 by 2/3. Actually, I'm just going to multiply to 1. And that equals root g. What is sine? Oh, okay. So what's sine theta then? If cos is 2/3. So quick triangle. Cos is 2 over 3. So that's 3 squared equals 2 squared plus something squared. So 9 equals 4 plus 5. So that's root 5 is that thing. So sine theta is root 5 over 3, and that's by t. And then you have g plus g over 2 t squared. So I'm just going to close some tabs here because it's not happy. Okay, hopefully that will do something for our animation. So what do we got there? So we have this mess now. And we can work out what the left is. It's 1.5 plus 1.5 by 2/3 is 2.5. So that's 2.5. Actually, and I'm going to bring it all over. I'm going to just rewrite this equation here. So we have 4.9 is our g over 2 t squared plus something horrendous it is root 5g over 3, just bringing both of those things into the root symbol, and then minus 2.5. Really hope the sound works on this because I don't have to do it again. So now we just use our minus b formula, which is on the front of your log tables should you forget. Apparently it's on the inside too, but I've never had need to look for it inside. So t is going to be minus root 5g over 3 plus or minus the square root of b squared, which is root 5g over 3 squared, minus 4 by 4.9 by 2.5. Extend that square root thing out there, all over 2a, which is 9.8. So I'm going to work out the determinant first, because if that turns out to be a negative, then I've made a mistake. So I just want to figure out if I've made a mistake or not first before I go on and do anything else. Don't think I have, but anyway. So it's 5 by 9.8 divided by 9 gives you 5.444444. That should have been a minus 2.5. There we go. I knew there's something coming up. So it's the square root of it's 49 over 9 there, and then it's 4 by 4.9 by 2.5 is 49, and that's plus 49, and that's all over 9.8. Now the marking scheme does it a lot neater than this because it cancels out stuff and keeps the g's in there, but sure, we're here now. So that's going to work. So we're going to get two answers. I hope that one of them will be thrown out because it's negative, but we'll see. So 5 by 9.8, and we're going to root that. Then we're going to divide by 3. That would be minus 7 over 3. And then it's plus or minus, it's 49 over 9 plus 49 is, and then square root that. And that's plus or minus 7 root 10 over 3. Now we can't take that away because if we do minus, there are two minuses, and then that gives us a negative. So we just need to worry about the plus case. So then you say, so it's minus 7 over 3 plus 7 by root 10 over 3, and then we divide that by 9.8, and we get 0.515 seconds, because t has to be bigger than 0. That's just horrible algebra. Like it's fine. It shouldn't be hard. It just who knows what's going to happen and who knows what the real answer is. So, but that's our t. And then the last part, which I don't think I copied and pasted, is, I think I forgot to do that. Yeah, I forgot to. So the last part is how far away is it? So I'll just draw it here. So if the thing falls and hits the ground here, what is this distance here from P to where it lands? So how that works is it's just projectile motion. We know how long it's in the air for. We can figure out we know the ux. So it's just ux by t. So ux is equals root g cos theta. And we just multiply that by t, and that gets us the distance the thing travels in the air. But this thing in the tail. So this thing is here, okay? At that x value, where the blue line is, that x value, it's in the air for this long. But how far away is it from P when it starts? I'll just highlight it in green. It's this far away when it starts, so we have to remember to add that on. Now this is only 5 marks, this whole thing, so I'd say if you got to ux by t, you'd get 3 or 4, but still. So see that there? That is how far it is away from P when it starts, and that is, because that's theta again, is 1.5 sine theta. Okay, cool. Hope that makes sense. Stop it and rewind and go back. But what we're going to figure out how far it goes while it's in the air and add that to how far away it was from P when it left the circle. So we know that ux equals root g by, we forgot, root g cos theta. So Sx equals root g cos theta t, which is root g by 2/3, because that's what cos theta is, and t is 0.515. And let's just get an answer for that one. So 0.515 by 2/3 by root 9.8, that's 1.07. So that's how long it is in the air. But that's not the question. The question, it says, and you can look at it, is how far away is it from P when it hits the ground? So what we have to do is add that. So the distance, we call it d, equals 1.07 in the air plus something else. And that something else was that bit in green up above, which is 1.5 sine theta. Oh, we worked out sine theta before, wasn't it? Root 5/3. Okay, cool. And again, go back and make yourself happy with that. So that's 1.5 sine theta plus our 1.7 we just figured out. So it's 1.5 by root 5/3 plus our 1.07, and I'll just, again, calculator that. 1.5 by root 5, then divide that by 3, then add 1.07, and you get 2.188, which gives you 2.19 meters. So hopefully the sound has worked for you on that one, and it's not too jumpy. I know the video seems to be very unhappy, but thankfully the text isn't doing much moving. So I'm going to just now quickly look through the marking scheme and then see where we got. So this is a total of 5, 10, 15, 20, 25, 30, 35, 40. It's 50 marks in total again. So it's 50 marks. So what do we get? So the assumption, 5 marks for the assumptions made. So that's, I'd say, it's just some of the assumptions. You don't need to do all of them. You can't do all possible assumptions, but kind of some of the big ones. And then if you've time at the end, if you want to add some more to it, just in case. But I'd say 2, maybe 3. So what we then get is, now it's a weird one that it is assumed you know that the energy needs to be conserved. So you don't get points for saying that. You get 5 marks for getting to here. So it's easy, but if you don't know it, you don't get a lot for it. Because the other thing is, this is also circular motion, so they have to give you marks for the circular motion stuff as well, and you get 5 marks for that one, knowing that the forces have to add up to mv squared over r. You get 5 marks for knowing when circular motion stops, when the particle leaves the surface, and that can be expressed in different ways, but just you need to show why that's happening or what's happening when it happens. Then you go all the way down here and you get 5 marks for this, for your cos inverse of 2/3. So right now I suppose we haven't done a huge amount of very difficult stuff, but we've got 25 out of 25. And we've got 50% overall so far. So then we calculate the velocity of the object when it leaves the surface of the cylinder. So that's mv squared over r when cos theta is 2/3. And that was 5. Now the markers, I just looking at something in the marking scheme there, doesn't make sense to me, but I don't think we need to talk about it. So then part 4 was, you got 5 marks for figuring out this god awful mess that I did there. You then got 5 marks for putting the distances had to fall equal to our S equals UT formula. And then you got 5 marks for this whole gobbledygook and for that there. And then this bit about the distance was 5 marks in total here. So overall, I think the last 20 marks, you should be able to kind of get 10 out of those 20 without worrying too much about